Hello everyone, so today we're going to be looking at a tutorial on Delannoy numbers and how to use them in MIPS as well as in Java. We're going to divide this tutorial in three segments. In the first segment we're going to be talking about what Delannoy numbers are. So basically we're going to talk about what is a Delannoy number, which is actually an algorithm. We're going to then write a Java code for it. Actually it's written, I'm just going to show you the code just to save time. And also after that, in the third segment, we're going to see how to write a MIPS code of it. But once again, the code is written. I'll just explain how I wrote that and the concept of it, the procedure, the mechanism of the code. So I'll try to link the timeline for this, and if any of you want to skip through any of this, like if you don't want to know what a Delannoy number is, skip through that. If you don't want to know what the Java code might look like, you can skip through that. So I'll try to mark the timeline on the video right here. So let's move on to the first segment of the tutorial. So first of all, what is a Delannoy number? Like I mentioned earlier, it's an algorithm. It's an algorithm that basically takes coordinates as an input. So Delannoy number actually works with the graphs. I think explaining Delannoy numbers will work best if we look at a graph first, like a grid. So as you can see here, there's a grid. I've made this 6x6 grid. So you have all these numbers written inside each of these nodes. The circles we're calling the nodes, and as you can see above each of the nodes there are x and y coordinates. So we're actually beginning, in this case we're beginning from the top left, that is 0 0 coordinate, and I actually began from the top left and I'm going to the right and the bottom, but you could begin from the bottom left, which is the more conventional way. That is because x moves right and y actually goes up, but in my case y goes down and x goes to the right. So this is actually the grid, and each of these numbers inside all these nodes are Delannoy numbers. What are Delannoy numbers again? Delannoy numbers is an algorithm that takes coordinates as an input. So let's say if I gave you 2 1 as a coordinate, my output should be 5. That's what Delannoy number is supposed to give me. And what does this 5 represent? Basically it means that there are 5 ways to get to this node, traveling from each of these nodes that are before it. Now of course there should be more than 5 if you travel all around the graph, but what you're talking about is traveling with a constraint, and the constraint being from the starting node you can only get to this node using the directions that are towards it. So as my starting node is 0 0 is above it, you can go down, right as it's to the right as well, you can also go right. So there are 3 movements that are possible. That is, one is going to the bottom, that is southwards, southeast, and then east. Of course, if you started from the bottom left, that would be north, northeast, and east. In this particular grid where 0 0 is at the top left, you can go south, southeast, and east. And we get the output basically by adding the values of the nodes, at the top of it, that is at the north, the northwest, and the west, which makes sense actually, because notice that each of the grids that have a 0 as one of its coordinates, like here x is 0 in all of them, and here y is 0 in all of them, each of these nodes have the value of 1, because you cannot go to any of these nodes except just going south. Because notice, if you go southeast, you have to come southwest. That's the direction you're not allowed to move in, traverse with in Delannoy numbers. So our only option is basically to go south. As for when y is 0, we can only go east. And if you notice, for any node, the only way to get to it is at first getting to the northwest node. For example, for 2 1, that is at 5. The only way to get to this node is basically either I have to come to this node first at the north, or I have to come to the node that is at the northwest, or I have to come to the node that is at its west, that is its left, or top. Once you get to these nodes, I have to get to the node that is 2 1. That's the only way. However we traverse through this graph, we have to get to one of these 3 nodes. So if there's per se 3 ways to get to the node to the left of it, one way to get to the node to the top left, and another way to get to the top, the only way to get here would be 1 plus 1 plus 3, that is 5. You can see that the node that is 3, it has 1 plus 1 plus 1, 3. Any node, like let's say 3, 63. It's written here, 63. So let's check. At the north, at the top of it, we have 25. At the top left, we have 13. At the left, we have 25 again. If we add 25 and 25 and 13, we get 63. 25 plus 25 is 50. And adding 13 to it gets you 63. So that's how the number works. That's the calculation of it. And basically for each input, like for example, if you get 2, 3, it says 25. 25 means the number of paths that we can take to get here, as long as the paths consist of 3 directions. 3 of them are allowed, which is basically down, right, and right. Basically all directions that are towards it, not away from it. And the grid here is starting with 0, 0 at the top left. It can also start with the bottom left or bottom right. It's up to you really. I think more conventional way is at the bottom left, but for this particular one we are looking at the top left, just a variation of the typical one. As long as you understand the meaning, we should be fine. So we will now move on to the second segment of the video, which is basically the Java code. So for the Java code, as you can see here, I've already written the code of it under a package Delannoy under the class solution. If any of you are using actually C or C++, the code will look pretty much the same. The only differences would be you'd be writing the main function, not any class or package. You'll be writing int main at this line, and then you won't have this scanner. See, you'll just have a scanf over here, taking the variables in A and B, and then you'll be calling the function here in your printf. This is basically Java's version of printing. And the method or the function for C, you will be writing the function just the way you usually write, int Delannoy, int A and B, and the rest of it would pretty much be the same. Yeah, so you can easily convert it to any language you want. Here we're looking at a Java code, and the code makes sense, right? It's very simple. Okay, what happened here? So yeah, like as you can see here, the main function, we're basically starting by scanning 2 values, which will be our coordinates basically. I'm sorry about that. So we're going to be taking in 2 values of the coordinates in A and B, and we're then sending A and B to the function or method. In this case for Java we call functions methods. So the method Delannoy, we send the 2 values as parameters A and B, and we print it right away. And what this function does is, if any of the 2 coordinates is ever 0, we return 1, and else what we do is we call the function again, and we subtract 1 from either the x. After that we subtract 1 from x and y, both of them, and we also subtract then y from y only, and we call all these 3 functions, and after we call that, it returns the summation of all of these 3 functions, everything that these 3 functions return. Once we have added all of it, we get the value of the output. So this is actually the recursion method. I'm assuming you already know what recursion is, so in that case you should be able to understand how this works. If you don't, that is a whole other matter. Tutors know about recursion, so I'm not going to explain that further than this. But if you understand recursion, you should be easily able to understand this one. It's a very simple code. It just keeps calling this function, and the value keeps getting subtracted. The next time it calls this one, for example, here if there's a minus 1 and b, and once again a becomes minus 1. It keeps happening until we get 0 here and we return a 1. Remember, if we return 1 here, you actually do not get to this line. So now we move on to the third segment of the video, which will be basically the MIPS code explanation. So we just opened the code of Delannoy, in the MIPS code of Delannoy written right here. It looks like a large code, and it is, as always, MIPS always makes the code large. I'll delete the comments that I had made during writing the code myself. These are not lines that you need at all, so I'll get rid of them right away. And basically this interface, if you're interested, the previous one in Java we were basically I was using Eclipse, and here we're using a simulator called Mars. If you can notice here, if you can read it, it's Mars 4.5 that I'm using. So you can use this. It's a very compact software. It's also portable as far as I know, and you can actually run the codes. It's very lightweight, it's a good simulator. So the MIPS code, here we're, as you can see under main, we labeled it main. That's unnecessary, but for understanding the context, we've written the label. We're taking inputs 5 and 5 in A0 and A1. We could be taking any inputs here. We're not doing scanf basically, we're just basically giving the number right away here, just to keep it simple. After that, we're basically calling the Delannoy function using jump and link. When we do get the value returned, we're not printing it, we're just going to check it at the output. When we run it, we shall show you right away, when I finish explaining the code. After we've seen the output, it exits. The exit label is basically here, so it jumps there and the code finishes. So the Delannoy function, at first what we do is we make room for four values in the stack. So as each values take 4 bytes of space, we are basically subtracting 16 here because we need room for 4 values. We keep the return address at the first offset of the address of the stack pointer, and then the A0 and the A1, the parameters basically, and then the return value, that is 0. So we keep all these 4 values together, and then we check if one of them is 0. If A1, the second parameter, is 0, we go to check 2, otherwise we jump to base case, which means, as you can see, it's BNE. So if it's not 0, it's true. If A1 is 0, for example, it will jump to base case, which is right here. At check 2, we check if one of them is, the A0 is 0. If it's not, it jumps to recursive, else it automatically comes to base case. At base case, what we do is we load the return address at the first offset of the stack, and then we load a 1 into the spot that we kept, like the 8th offset. That is basically one, like the first one is 0. Sorry, I mean the 12th offset, my bad. So the first offset is supposed to have the return address, then the 2 parameters, and then the 12th offset will have the return value for V0, right? So we set V0 to 1, we save it at the stack, the 12th offset of the stack pointer. Afterwards, what you do is we add 16 to the stack pointer just to get rid of the data at the stack, because we do not need them anymore after this point. And then we jump to the return address that we had just loaded. What happens is it returns to the address where it was called at first. So think about it, if 55 was sent here, it will of course first of all go to recursive, and recursive will add -1 right here to the first parameter. So we're subtracting 1 from A0 and storing it at the destination A0. So then we are calling the function again. We're saving those values, which will give you 4, 5. It'll be subtracted again. Once again, the function will be called until it becomes 0 at recursive, right? When it does become 0, we're calling the function again, and 0 gets stored, and then this one will become true at first. And when that happens, actually this will become false because we're using BNE. So when this becomes false, that means A0 is 0, which means we jump to the base case right away and we get a 1 at V0. When we do the jump to the return address, we actually come back here because the address that was being stored is basically linked right here. So we come back here. What we're doing is loading the value at the 12th offset of the stack pointer at a temporary register, and then we're adding V0 to it and storing it at V0. We're then saving the v0 at the 12th offset of the SP. So we're returning the value after having added the v0 that was returned here at the base case, which is 1 in this case. We're adding the 1, sending it back to the SP, the stack pointer at the 12th offset, and then we're loading A0, A1 to subtract 1 from them, both of them again, which is actually the part, as you saw in Java, the second part of the function calling. We send A-1, B-1. So we do that, then we again call the function. Once again they get stored, so you get 4 4 and then 3 3 2 2 1 1 0 0 until you get 0 0, and then you get to the base case, you get the return value of 1 again. You store it to the SP, and then this part is actually necessary because it gets lost right away. Remember, the v0 is the one who's holding the value. So when we come back to the return address, this time we were linking this one, so we come here, we load the value of the 12th offset again at t0, we add v0 to it, save it at v0, and then save the value of v0 to the 12th offset of the stack pointer. And then we load the A0 and A1 again, this time subtracting 1 from A1 and then calling the function again. So this time we're actually doing this one, that is, we're subtracting B-1. And then after that we load the return address, because this was actually the last call right here. This is actually the last function call. After this we're going to be returning again somewhere. So we take the return address that is stored, we basically once again load the value of the 12th offset of the stack pointer to a temporary register, that's t0, we add v0 to it, save it to the 12th offset of the stack pointer again, and then get rid of the data by adding 16 to the stack pointer, because we do not need those immediate 4 datas here anymore. And then we jump to the return address, which eventually would lead to this point here, like here exactly. So when we return to the return address, we jump to exit and the program finishes itself. So that's actually how Delannoy works. So if we check for the values, let me try running it in Java first. For example, if we run this code and we enter 5 5, the value is 1683. If you run it in Mars, it's saved. Remember, if you're going to run a code in Mars, you have to save it first. It is saved. After that, you go to run and assemble. So if you run the code, if you notice at v0 the value is 1683. Let's try changing that. Let's try a different value. Let's say 3 4. 3 4 should be fine. 3 4. That is 129. So for MIPS, let's make this 3 and make this 4. Save it, assemble it, and then run it. As you can see here at v0, the value is actually 129. So it's working. And if you check the charts now again, the chart looks somewhat like this, yeah. So at 3 4, that'd be x3 y4. So here we have the value 129. So that is it for Delannoy numbers. Now let me just say something. This is a very advanced topic, kind of. Not very advanced, they're basically very basic of MIPS. I haven't used any much of anything complicated. I'm actually learning MIPS for it's been like a month or something. So anything that's here is something I've learned just recently. So if you know the basic of MIPS coding, you should be able to understand all of this pretty well. If you don't, you need to learn MIPS for this first. Maybe I'll provide a tutorial for that later on. But this is rather a bit advanced, and I would like to apologize if I moved too fast. But I hope you would be able to understand how the MIPS coding worked. And I'll try to provide the code files, the ASM file for the assembly, the MIPS code basically, and the Java file at the description. Basically, I'll provide a link to it in the description, or perhaps right in the code itself. Either way, you'll have the code to run, to test. And another thing about MIPS is basically, after assembling it, you could run step by step. let me show that once. Like here, we're basically this line we're adding 0 and 3 to A0, which means we're storing 3, we're storing 4. We're calling the function which immediately moves to the stack pointer. We subtract 16 from there. Notice that the SP we have the value 2147479548. 16 subtracted from that would make the last two digits basically 32. No, sorry, not 32. Yeah, it will be 32. I was right. So anyways, so as you can see, it becomes 32, and then we store the array at that address. If you can see here, this is 20 plus 0 plus 4 plus 8 plus 12. 20 plus 12 is 32. We're storing it at the return address here, which was the address of exit, which you can see here, 4194316, which is 4194316. Then we store the parameters 3 and 4 at the stack. Then we store 0 at the v0. So we go ahead, we check if it's 0 or not. We subtract 1. You can see A0 becomes 2, and you can see all these changes. So stack comes right here, and the values of the registers are right here. And if you just check it through, if you run step by step, you can actually watch the simulation yourself, and you can figure out how the things are working. So hopefully once you have the files, you'll be able to understand the code better. And so that's it actually for the tutorial. I hope all of you learned something from here, and thank you for watching. I'll also try to provide another example of a similar code of MIPS. That is basically, I'm going to be doing a video on Fibonacci. If you have any questions, you can go ahead and ask them to me in my comments. I'll try to answer them as soon as I can. And I'll also try, and also if you have the suggestions, like maybe I did something wrong, maybe I did something right, you can just say whatever you want in the comment basically. Anyways, thank you for watching. I hope you learned something from the tutorial. See you again next time.